Think about this for a second. How does your GPS actually know your exact speed right now? I don't mean your average speed for the trip, I mean at this very instant. Or, how do engineers know for absolutely sure that a massive steel bridge won't collapse under rush hour traffic? How does a doctor read your heart rate just by looking at a squiggly line on a monitor? And, going back a bit, how did NASA calculate the exact split-second moment to fire a rocket so they could land safely on the moon? Every single one of these everyday miracles requires immense, precise calculation to even function.
Well, welcome to this explainer. I am so incredibly thrilled to have you here because today we're uncovering a massive secret. Every single one of those completely different questions we just asked, they all have the exact same answer: calculus. And today we're going to look at exactly how it works. But don't worry, we're not doing textbook math here. We're explaining it entirely through real, concrete, vivid examples from our physical world, which makes every single concept feel immediately obvious and totally alive. Let's dive in. So, to understand how we measure a constantly changing world, we have to start with one foundational idea: the limit. A limit is simply what a value approaches as something gets infinitely close to a specific point without ever actually exactly reaching it. It sounds simple, right? But it is absolutely crucial. It's this core concept of getting infinitely close that makes literally every other tool we're about to explore possible.
Let's jump right into example 1, the speeding car. Picture yourself driving down the highway. You know you've traveled a certain distance over a certain amount of time, and if we map that out, we get a smooth curve showing your position. But here's the question: how fast are you going at exactly this moment? Not over the whole trip, just this precise split-second instant. That answer is your exact reality right now. And spoiler alert, that's exactly what a police officer's radar gun is looking at when you're hoping you don't get a speeding ticket.
That key distinction between an average rate and an instantaneous rate, it is everything. If you want to know your speed at that exact isolated second, mathematically, you draw a tangent line, a line that just perfectly grazes the curve at that exact point. That line gives you your answer. That line is the derivative. A derivative continuously calculates how fast a quantity is changing at any single specific instant.
And the derivative is truly the heartbeat of real-time data. This hidden mathematics is exactly how your dashboard speedometer knows what number to show you. It's the engine inside that police radar gun. It's how self-driving cars calculate their instant velocity so they can make those life-or-death, split-second safety decisions. Whenever you need to know the absolute reality of right now, you use a derivative.
Okay, let's shift gears to example 2, the cooling coffee. Imagine a steaming, hot cup of coffee just sitting on your kitchen table. You know what happens, right? It cools down really fast at first, and then, as it gets closer to room temperature, that cooling slows way down. If we plot that, we get a curve that drops steeply at the beginning and then smoothly flattens out over time.
Now, finding the exact rate of that cooling, that requires our good friend, the derivative. The derivative of this specific curve tells you exactly how fast the coffee is cooling at every single moment as it goes through what we call exponential decay. We aren't just estimating here. You can pinpoint the precise rate of temperature drop right down to the millisecond.
And this isn't just about your morning brew. This exact same mathematics describes how medicines decay in your bloodstream, which is how doctors know exactly when to give you your next dose. It predicts how radioactive materials break down over centuries, and it even tracks how global populations rapidly grow and shrink. It's all the exact same math. All right, let's move to example 3, draining a tank. Imagine water rapidly rushing out of a massive industrial tank. We know the flow rate at any given moment, but here's the catch. Because the water pressure drops as the tank empties, that flow rate is constantly changing. So how do you figure out exactly how much total water has actually left the tank? Normal, simple multiplication totally breaks down here because the rate just won't stay still.
To solve this massive problem of continuously changing rates, we use the integral. Now, an integral is the total accumulated amount that you get by adding up an infinite number of infinitely small pieces. Sounds wild, right? But by continuously adding up all those tiny, ever-changing amounts of water leaving the tank at every single instant, the integral perfectly and exactly calculates the total volume drained.
This concept of infinite addition is happening all around you, right now. It's how fuel consumption in a massive commercial aircraft is calculated mid-flight while the plane's weight is constantly dropping. It's how civil engineers predict river overflow during a major hurricane. And, bringing it closer to home, it's exactly how your smartphone carrier calculates the total data you've used when your download speeds are fluctuating wildly all day long. Now lean in for this one, because here is the absolute most powerful secret of calculus.
The fundamental theorem of calculus states that differentiation and integration are inverse operations. That means they completely undo each other. They aren't just isolated, random mathematical concepts. They are quite literally two directions on the exact same street. It's brilliantly simple.
We can actually use these inverse tools to optimize our world. Take example 4, the bridge curve. When engineers design a massive steel bridge, they absolutely must know exactly where the maximum stress on a beam is going to happen so the whole thing doesn't collapse. Well, if you plot the physical stress as a function along the length of that beam, the point of maximum stress is found exactly where the derivative equals 0. It's the very peak of the curve. And guess what? This exact same technique is used to find the minimum cost in economics, the maximum profit for a business, and the safest, most efficient flight path in commercial aviation.
Example 5. The heart monitor. Reading rates of change from real data curves.
Picture a tense hospital room. You've got a doctor standing there reading a patient's heart rate from that glowing, squiggly line on a monitor. We've all seen it. But that ECG trace isn't just a simple drawing. Every single peak, every steep slope, and every subtle little curve contains critical, life-saving medical information. But human eyes aren't enough. Doctors need mathematics to decipher it instantly.
By applying calculus to that real-time data, the machine itself does the heavy lifting. The derivative of the ECG signal tells doctors exactly how fast the heart's electrical signal is changing at any microsecond. This precise, continuous mathematical calculation is exactly what allows the monitor to instantly detect dangerous arrhythmias, impending heart attacks, and irregular beats the very moment they begin.
What that really means is that calculus is running silently inside every single medical imaging machine in the world. Every MRI scanner mapping out your internal organs, every ultrasound tracking a baby's development, and every modern diagnostic device out there relies heavily on these mathematical operations to translate continuously changing physical signals into crystal-clear medical insights.
So when we pull back the lens, the big picture here is just breathtaking. Every single time something changes, a car's speed on a highway, the temperature dropping in a cup of coffee, a global population shifting, an economic price fluctuating, or a human heartbeat, calculus is the mathematics that describes, predicts, and controls that change with absolute precision.
Calculus is not some abstract subject that you study in a dusty textbook and immediately forget. It is literally the hidden language of every moving, changing, living thing in the entire universe. So I want you to remember this incredible, continuous mathematics happening right in front of you every single day. Look around. What other hidden calculus is running the room you're sitting in right now? Thank you so much for exploring this with me today, and as always, stay curious.